Hello everyone, this is Group 2 and we are presenting our project on image compression using SVD. Next slide please. So this is the basic background of our topic and we are using SVD and QR algorithm to decompose the image and we are using that to compress the image. Next slide. The motivation to take this topic was that the compression speed is high and it is more stable, unlike Fourier series, and it does not lead to ringing artifacts. This is the basic problem statement. The basic mathematics of this topic is we are dividing an M cross N image matrix into M cross M, M cross N, and M cross N matrices using SVD. And then we are arranging this SVD singular values in decreasing order. Next slide. So the matrix U will form an orthonormal set. The columns of matrix V will also form an orthonormal set, and the diagonal matrix S will have singular values in decreasing order. Next slide. The basic mathematical concept of QR algorithm is also used to calculate the eigenvalues and eigenvectors. So it becomes difficult to calculate eigenvalues and eigenvectors of matrices of dimension more than 2 cross 2. So we are using QR here to calculate that.
Talking about the literature survey, so the image compression is done by removing some redundancies such as coding redundancy, interpixel redundancy, and psychovisual redundancies. Next slide. So there are some terms like compression ratio, which is the ratio of the space of original image to the space of the compressed one. And there is the concept of eigenvectors and eigenvalues, which we have used. Also, SVD is a lossy compression, which means that after compression, the data that is removed is permanently lost. Next slide. So these are some properties of SVD. Next slide. So S A is equals to U into S into V transpose. So we are multiplying each matrix which has rank of R to get an image matrix, but in the compressed image, we are taking the value as K instead of R, such that K is less than R. So this is how it looks like after taking K. And next slide. So the dimensions become M cross K, K cross K, and K cross N. Next slide. So the memory of the compressed image will turn out to be K into M plus N plus 1 instead of M cross N. So the compressed ratio would be Mn upon K into M plus N plus 1. And MS is as follows. Next slide.
Okay, so till now we saw what image compression is and how it can be achieved using SVD. We also saw some properties of SVD and the relationship between the value of K memory and compression ratio. So in continuation of that, according to the research paper, in order to save memory, we can discard some singular values and that will avoid causing too much distortion. As we also saw previously, how the value of K depends on the memory and the compression ratio. We can again observe that as the value of K increases, the image quality will increase and the compression ratio will decrease. And this is the basic idea about the QR decomposition that is used to find the eigenvalues and eigenvectors. And yeah, so now we'll see some of the reproduced work that helps in performing image compression. So for the grayscale images, we use a MATLAB simulation where it takes little time to get the desired output. So basically, we convert the grayscale image into matrix form and then perform SVD on it, which yields us compared images. Note that we have used 15 different K values so that the image quality can be, the difference could be seen clearly. As mentioned before, it proves that as the value of K increases, the image quality becomes clearer. We also plotted a graph which compares the error in the compressed image with the number of singular values used. And this is a flowchart for the MATLAB simulation. And now talking about the RGB components, so we'll follow the same procedure. We'll separate the RGB components and we'll perform the QR decomposition to find the eigenvalues and eigenvector, and we'll call the SVD function, and then we'll calculate the mean square value error. This is the image for the original and compressed. You can see the difference clearly. The value of K taken here is approximately 11. This is a graph between the value of K and the mean square error. And this is the flowchart for the RGB component. And yeah, that's it.